Hello, students. Welcome to the NMR Lecture Part 2. So if you'll recall, last time we talked about the hydrogen nucleus and how if you put it in a magnetic field, your hydrogen nucleus will line up either with the field or against it. And in addition, if you blast it with exactly the right frequency of light that happens in the radio wave part of the spectrum, you can get this hydrogen nucleus to flip from up to down or down to up. That particular frequency of light is the resonance frequency, symbolized by the Greek letter nu. And in NMR, we call that resonance frequency the Larmor frequency. So the Larmor frequency is just equal to gamma times b over 2 pi, where gamma and 2 pi are just constants. And b is the strength of that external magnetic field that the hydrogen is experiencing. And so the Larmor frequency is directly proportional to the magnetic field. And of course, where we left off last time, physicists noted that for pretty much all of the different samples that they tested, the hydrogens had basically the same Larmor frequency. They were different a tiny little bit, but mostly the Larmor frequency for the hydrogens in water was pretty much the same as for ethanol or acetone or pentane or other compounds. And physicists thought, hey, that's pretty darn cool. It's a universal thing about hydrogens. Look, isn't physics neat? And chemists were like, why are they almost the same but slightly different? And if they are slightly different for some valid reason, maybe it's related to the differences in chemistry between water and ethanol and acetone. And maybe we can exploit this difference to tell us some interesting things about their chemistry. So this next phase is about what those differences are and why they're interesting and important. All right, let's talk a little bit about atoms in a magnetic field. So the question is, why might different hydrogen nuclei resonate at slightly different frequencies? What might be different about the hydrogens in, say, for example, methane, CH4, versus water? Remember that the frequency, that Larmor frequency, depends only on the magnetic field that hydrogen is experiencing. So let's first start with a uniform applied magnetic field. We'll call that our B field, or B applied. This basically means we're taking our sample and we're sticking it in between the poles of some giant magnet. In modern NMR, this is a superconducting electromagnet. Let's start with a neutral hydrogen atom, which of course is one proton and one neutron. There they are. Proton is there in blue. The electron is there in red. And of course, you'll remember from physics that the electron is in motion. Now, this next part is a little bit complicated, and I'm going to skip discussion of the Lorentz force law and the right-hand rule and all that stuff. I might make a separate video if you love physics and you want a detailed explanation. But basically, what happens is when you have a moving charge in a magnetic field, that electron will race around in circles, right? So that applied magnetic field causes the electrons to circle around in these big circles around the nucleus over and over and over again, as long as that applied magnetic field is in operation. And what's interesting about that is essentially we've created a little tiny circuit, and circuits of flowing charge actually create their own magnetic field, right? So this electron spinning around in circles creates its own tiny magnetic field. It induces that field, and that little magnetic field created by the electron is always opposite the direction of the applied magnetic field. And we call that little tiny field that's generated by that electron zipping around, we call that B local. So B applied is the main the main magnetic field that is created by the magnet that we're using, the external magnet. And B local is a much smaller magnetic field in the opposite direction that's created by electrons as they spin around in that magnetic field. And of course, as you might imagine, if you have more electrons, let's say you added a second electron to this hydrogen to make it H minus, if you have two electrons, they're going to spin around and the size of B local actually increases. Did you check that out? Check out the arrow, right? So this would be the arrow for the magnitude of B local for one electron. You add more electrons, oh, boom! Suddenly B local gets bigger. I know my PowerPoint animation skills are amazing. All right, so let's keep that in mind. We're going to the next one. So let's ponder this. Let's return to some observations from earlier. Number one, as we mentioned, these hydrogen nuclei can spin flip when you hit them with a radio wave at exactly the right resonance frequency. That's known as the Larmor frequency. Physicists noted that every hydrogen that they tested had basically pretty much the same Larmor frequency. The difference between the different samples were a few parts per million, right? So they're mostly the same, but just very small fractional differences. Chemists were thinking, yeah, but why do these differences exist? They must be caused by something. And what can they tell us about these different compounds? Right? So for example, why is the Larmor frequency of HF, hydrogen fluoride or hydrofluoric acid, different from H2? So the question that I want you to ponder is, which one will have the higher Larmor frequency? Which one will have the higher Larmor frequency, HF or H2? Remember that the Larmor frequency basically is directly proportional to the magnetic field that these nuclei experience. But the question is, what magnetic field, what B, is the nucleus actually experiencing? If we're talking about this blue nucleus right here, is it B applied? Or is it B local? Or is it something else? Ponder that for a minute. Pause the video for a minute and just think about what magnetic field this little blue nucleus is feeling right now. Okay, did you think about it? The nucleus, of course, is feeling both of those magnetic fields. It's feeling B applied, and it's also feeling B local, right? So really what it's feeling is the net magnetic field created by both of them. And notice, remember that B local is always in the opposite direction from B applied. So as B local gets bigger and bigger and bigger and bigger, the net magnetic field that nucleus is feeling goes down, right? So really, if we were going back to this equation right here, the Larmor frequency is directly proportional to B net, right? B net is the net magnetic field. When you take the applied field and you subtract off the local field, right? The net magnetic field really is what determines the frequency that will flip this nucleus up and down. Okay, remember also that B applied is usually way, way, way bigger than B local. B applied is caused by this huge superconducting electromagnet. So it's very, very, very large. B local might be 1,000,000 times smaller because B local is just caused by these electrons circulating around. And if it's 1,000,000 times smaller, that means if you look at B net, right, B net for different types of hydrogens is only going to be different by a few parts per million. So let's go back to this question that we just looked at. We can use this idea to figure out if HF or H2 will have the higher Larmor frequency, right? So F has a lot of electrons, but it is also very, very electronegative, the most electronegative element in the universe. And it will pull on those electrons and pull all of the electrons around the H away from the H and towards the F. So think about this. Here's our HF. Here's our H2. Spend a minute and see if you can't figure out which one has the higher Larmor frequency, HF or H2. Remember that the Larmor frequency is directly proportional to B net. So think about which one is going to have the bigger B net. Pause the video until you can figure out until you can predict which one has the higher Larmor frequency, HF or H2. Okay. Let's look at this. The H in HF has less electron density around the nucleus. Why? Because that fluorine is pulling electron density away from the H, which gives it a partial positive charge. If there's fewer electrons flowing around the H in HF, what does that do to B local, right? If there's fewer electrons, that means B local is going to be smaller. If B local is smaller, then B net is actually going to be bigger, right? B applied is the same in both cases. But if the B local is smaller, then B net's going to actually be bigger, which means that HF is going to have the bigger or larger, the higher Larmor frequency. So why is NMR so important for chemists? Let's wrap this up. Here we go. So NMR, this new technology, this form of spectroscopy, can measure the Larmor frequency. That's what an NMR instrument does. The Larmor frequency, remember, measures B net. It's a way to sort of probe to see how strong of a magnetic field is that nucleus experiencing. B net, of course, changes depending on B local. B applied is usually the same, but B local is changing for different compounds. B local depends on the number and type of nearby electrons. So why are electrons important for chemists? Electrons, you'll recall, are where the chemistry is at. If you look at the periodic table, remember the periodic table is arranged based on electron configurations, right? When you have various reactions, the reason why those elements are different, why they have different chemical and physical properties, it's because of the electrons. If you think about bonding, what are bonds? Bonds are electrons, right? So electrons are where the chemistry's at. So now we're excited, right? NMR can actually differentiate different hydrogen nuclei based on their different electronic environments. Different chemical compounds have different electronic environments, so NMR is a way that we can tell one compound from another, right? So NMR is a probe to give us information about electrons, and electrons give us information about the chemistry. And if different chemicals or different substances have different electrons, they're going to have different NMR signatures, and that's what we're going to use as our tool. So this is the significant, this part in bold is the big so what. If you've been waiting for, 33 minutes now through this lecture to get to the so what part, this part in bold down here at the bottom, this is the so what. This is why I'm going to ask you to spend another couple weeks in this class learning about NMR. All right, here is a super simple picture of NMR spectroscopy. Okay, going back to our general image or model of how spectroscopy works. First of all, I'm going to take a sample that I want to study, and I'm going to put it in a magnetic field. So let's suppose this is my sample, and I want to know some information about it. I'm going to stick it between the poles of a giant magnet. Oh, wow, that is, I know, thank you very much. That is the best magnet I know you've ever seen. Here's the South Pole, here's the North Pole. The lines of magnetic field are going that way. When we do that, remember, what happens to the hydrogens? When you put them in the big magnetic field, they will line up either with the field or against it. So this little up arrow right here represents a hydrogen, a nucleus in my sample, and it's lined up in the same direction as the field. So check, that's the first step. Check, step 2, this is spectroscopy, which involves light. So we're going to use light, not visible light from a flashlight, but this is, think about it as sort of a metaphorical flashlight, a flashlight that can emit radio waves. And we're going to turn on that flashlight, and some light is going to be directed towards my sample. All right. Let's suppose for a minute that that light is not the correct resonance frequency. If it's not the correct resonance frequency, it does not get absorbed. It just passes straight through the sample and comes out the other side. If the light doesn't interact with the matter at all, then what will the detector see? The detector will just see the exact same light that was being emitted from the flashlight in the first place, right? So if the detector is like, yep, I see that light, then nothing is happening. What we're going to do now is tune our radio wave source. So we're going to adjust it so now it's actually emitting a slightly different type of radio wave. Radio waves have slightly different frequencies, and we're going to see if those react, right? They might pass through, still nothing happens, so we adjust it some more. Nothing happens, we adjust it some more. Eventually, if we keep adjusting it, we're going to get to the resonance frequency. And remember what happens when this hydrogen gets on resonance, something will happen, right? Predicted by our Larmor frequency equation. When the Larmor frequency is exactly right, then, oh, did you see that? The nucleus, check out what's happening in that green beaker. The nucleus flips from spin up to spin down, and back to spin up, and back to spin down, right? So now it's on resonance. When that happens, that's actually absorbing some of the light energy that's hitting the sample, right? And so if some of the light energy gets absorbed, then, ooh, did you notice what happened over there, right? So there was light reaching the detector, but now that we're on resonance, some of that light goes away, right? The light is attenuated. Some of it is absorbed by the sample, right? So the detector is like, whoa, The light is gone. Stop everything. Hold on to your hats. We must be at resonance frequency. Please mark this down, spectrometer, because we've determined the exact frequency that is the resonance frequency for the hydrogens in this particular sample. Right? So it records that. The computer matches up the signal with the corresponding frequency, and ta-da, it makes something that looks like this. So this is a very, very simple NMR graph. The numbers along the bottom represent the frequencies in parts per million. This is methane, CH4. Methane, as it turns out, only has one Larmor frequency. All these hydrogens are the same as each other. And this bloop, big peak represents whatever that frequency is. And you can see, you can read off the graph, this frequency is about at 0.9, 0.95, almost 1. And we'll talk in the next video about what does that mean, like 1 what. I should tell you, of course, that this is sort of a simplified version of how this works. It's a little bit actually too simple. That modern type spectroscopy is a little bit more complicated. And later on, we're going to talk about what's called pulsed NMR and using the Fourier transform. So what I've just described to you is what we call a continuous wave NMR experiment. It's how NMR was used in the 1960s, 1970s, even into the 1980s. And then starting in the 1980s and 1990s, we discovered more powerful ways to do the same type of experiment. It's the same basic idea, but we used pulsed forms of light and this cool mathematical tool called the Fourier transform. So more about that much later. And in our next video, we're going to talk about, okay, now that we have this theory, how can we actually use this to figure out what the structure of compounds are and to identify compounds where we don't know what they are. So stay tuned for that.